In this video, we're going to talk about Green's theorem, and we're going to start with some definitions about curves. We'll say that a curve is simple if it has no loops, and we'll say that a curve is closed if the start point equals the end point. So let's draw some pictures. Something like this is simple. Something like that, oh, there's a loop, so that's not simple. Closed means whatever your start point is, your end point is going to be at that same point. So that's a closed curve, and that's in fact a simple closed curve because it has no internal loops. Whereas something like this, oh, there's a loop and the end point is equal to the start point. So that would be a closed curve, but not simple. One final definition around curves, we say that a simple closed curve is positively oriented if the region R remains on the left as we travel along our curve C. So let's draw a picture to understand that. So let's say here's our curve, which we'll call C. R is the region that's enclosed by the curve. And positively oriented, the curve is positively oriented if we travel along C this way. So if you imagine you were actually walking along the curve this way, your left arm would be pointing into the region. So you could say the region remains on your left as you travel along C. If you were actually going backwards, so imagine if you were going this way, then the curve would be negatively oriented and you'd have the region on your right as you travel along C. So there's our positively oriented curve. And if you want a more intuitive way of thinking about this, you could say positively oriented means the curve is going in a counterclockwise direction when you're viewing it from above. So here is the statement of Green's theorem. We're going to let C be a simple, closed, positively oriented curve that bounds a region R. So let's draw a picture to get going here. Here's C. Simple and closed, it's positively oriented, so it's going this way. And that encloses a region R. All right, main idea of Green's theorem is that we're able to turn a line integral into a double integral over the region R. So line integral around our curve, same thing as the double integral over a region R of a specific integrand. Now notice that this line integral here has this little circle on it. That means it's a closed line integral, and that's just a way of indicating notationally that our curve C is closed. So it's just emphasizing that we're integrating around a closed curve. Let's think about a physical interpretation of Green's theorem so that we can understand that on an intuitive level. So let's say that we have a vector field. It's in 2D. We'll call that PQ. And specifically, let's say that's a force field. So when we look at the integral on the left side here, that's the integral around C of something that looks like p dx plus q dy, that is work. So that's the work done by our force field around C. And then let's look at the right side here. Specifically, let's focus in on this delta q by delta x minus delta p by delta y. You might recognize that as being the z component of the curl. So we're taking this z component of curl of our vector field, we're multiplying that by dA, which is a tiny little chunk of area in the xy plane. Okay, and then to say that we're integrating over R is really like saying we're taking an infinite sum of quantities that look like this. This infinite sum is over infinitely many tiny rectangles dA. And for each of those little rectangles, summing up the z component of the curl of f times dA. So let's see if we can draw a picture of that. So here's our curve. The region R is this enclosed region. We're breaking this region up into these little tiny rectangles, infinitely many of them. Imagine your force in this neighborhood is acting like that. So what's going to happen is that you're going to have lots of cancellation in the interior, because if the force is acting this way, you're going to have a rotation that's induced in this direction around this point, but then around a neighboring point, you're going to have a rotation that's induced in the opposite direction. So lots of cancellation in the interior. And that implies that we're being left with the net effect on the boundary, which is C. So the sum here is just leaving us with the net effect on our actual curve. Okay, now if we want to think about what this net effect is, probably the best way to think about that is to just analyze the units here and confirm that this net effect that we are seeing on the right side really does give us work. So let's think about units. Let's start talking about units for our vector field. We said that in this example, our vector field is a force field. So units would be newtons. We know units for work would be newtons times meters. And then let's start to look at the right side here. Let's talk units for curl of f. Okay, well, to calculate curl of f, we had taken a bunch of partial derivatives of our vector field with respect to the coordinate axes. So units for curl of f, you'd just be taking your units for your vector field and dividing by meters, dividing by units of your coordinates. And then that z component of curl of f is being multiplied by dA. Units for dA would be meters squared if x and y are being measured in meters. And so that right side then, if we look at this quantity here, units for that right side, or it would be newtons per meter times meters squared. So sure enough, that's giving us newtons times meters, which is units for the left side. So that's how we know for sure that this net effect that we're getting on C from looking at the right side really does calculate work. So with that, let's try an example of Green's theorem. So we are going to evaluate the following line integral where we've got a description of the curve that we're integrating around. It's the positively oriented curve bounded by y equal x and y equal x cubed. So maybe we could start by drawing a picture of C. So here's our line y equal x, and our curve y equal x cubed would look a little something like that. After drawing the sketch, I realized that I needed to add a little clause here. So we actually want C to be the positively oriented curve bounded by y equal x and y equal x cubed in the first quadrant. So that way we can see that we're just focusing on the first quadrant portion of this diagram here. And we're capturing this curve here formed by part of y equal x cubed and part of y equal x. Okay, now we know C is positively oriented, or in other words, counterclockwise when we view it from above. So that means we're traveling along C this way and then that way. So you can think of this as saying if you're walking along this curve, the region R, which is this region here, would stay on your left-hand side. Now, if we were going to evaluate this line integral directly, then we would need to parameterize the portion of y equal x cubed, parameterize the portion of y equal x, and then sum up the two line integrals over those two different curves. But Green's theorem is going to allow us to vastly cut down on the amount of work here. So I think I'll write down Green's theorem towards the bottom of the screen just so we remember what we're trying to do here. Green's theorem says if you are taking the line integral around a closed curve, as long as it's a simple, closed, positively oriented curve, and what you're trying to integrate is something like p dx plus q dy, then you can rephrase that as a double integral over your region. And what you're integrating, it's the z component of the curl, so delta q by delta x minus delta p by delta y. And then we've got our dA at the back there just to emphasize we're doing double integral over that region. So a couple things we need to get done. We need to figure out our integrand here, and we need to figure out the region R. So let's start with our integrand. When you have your line integral written in this form, P is just a name for whatever's being multiplied with the dx, and Q is just a name for whatever's being multiplied with the dy. So let's calculate our delta q by delta x minus delta p by delta y. So that is delta by delta x of 2x cubed plus 6xy squared minus delta by delta y of 2y cubed. Okay, so let's get that figured out. That's going to be 6x squared plus 6y squared minus 6y squared. So in other words, our integrand is just 6x squared. So that sounds pretty nice. And then the other thing we need to do to be able to plug into our double integral on the right side here, we need to just express our region R nicely. So looking at this region, I say vertical slices would work just fine for capturing all the points in that region. these two curves would intersect when x equal 1. And so in capturing your vertical slices, you could say each vertical slice is going from y equal x cubed at the bottom to y equal x at the top. Remember, with vertical slices, we talk about the y values first. And then as we scan over our region from left to right, x would be going from 0 to 1. And if we're doing vertical slices, then our dA is going to become dy dx in that order. So with that, we're going to plug everything into the double integral, and that's going to allow us to completely avoid having to deal with the line integral. So our integrand we said was 6x squared, dA was dy dx, and limits for integration, we said y was going from x cubed to x, while x was going from 0 to 1. Okay, so let's get the integration done. Keep our outside integral on there. Integrating with respect to y, we'd have 6x squared y, and that's going to get evaluated at y equal x, and then y equal x cubed. So we keep our integral and our dx on there. Evaluating, we'd have, well, I'm going to bring the 6 outside, I think. We'd have x cubed minus x to the 5th, and then we can integrate with respect to x. So x to the 4th over 4 minus x to the 6th over 6, and evaluate at 1 and then at 0. So inside the brackets, we're going to have 2 over 24 minus the value at 0 is just 0. So for our final answer, we're getting 12 over 24, or let's just call that 1/2. So let's really appreciate the power of Green's theorem here. We did not need to parameterize our curve. So we were able to evaluate our line integral by an indirect way. Green's theorem says, hey, you can switch this over to a double integral over the region R if you prefer. As long as your integrand is relatively easy to integrate, and as long as your region R is fairly nice to set up, then that double integral will probably be more efficient than calculating the line integral directly. So that's all about Green's theorem. Thanks for watching.